So everybody knows how to find averages, right? I mean, in general, when you want to find an average, you just add the number of terms and divide, add the different terms and divide by the number of terms, and there goes your average, okay? So for example, if we have some discrete space in which a function is defined, then if we want the average of the function that's described in evenly spaced points, we'll have, f at the first point plus f of the second plus dot 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 to f of the last point, and you divide it by the number of points, okay? So that's pretty intuitive. And we could write n as, we could write delta x as b minus a over n when we break up a subinterval. And so you'll get this over here, and this is what you get if you have a function that's defined discretely, a discrete number of points, basically, okay? Now your very typical discrete interval is the integers, right? You just take the first point, x sub 1, plus the second point, x sub 2, plus dot dot dot, x sub n, the values at these different integers, and you divide by the number of integers. Okay, it's like saying if someone, if you want the average height between 5 people, you take the heights of 5 people and divide by the number of people. Okay, so this is similar to that because it's the discrete case. Okay, here of course we're looking at the real interval, which makes it a bit different, but we're still in discrete case. Now what happens when we take the limit as delta x goes to 0 or that n goes to infinity? So you're taking the number of points to infinity that you sort of sample at. Well, you get an integral. Here is the average of a function, okay? And that is quite remarkable, right? Because you're not just adding a discrete number of points. So you're taking a whole sort of continuous values. Okay, and the definition of average value here is this, okay? And we could write something like, f bar, it wouldn't be wrong to write this as a, b, because that is part of, the average is defined as an average over an interval, okay? And so here is the formula there. Well, here's a very important theorem that uses the concept of average value. The mean value theorem for integrals. Okay, now you've probably run into the mean value theorem before in prior studies on derivatives. And, the mean value theorem before was basically telling you that the secant line over a certain interval, you could find a function that has a derivative. Okay, that's you could find a point on an interval such that the derivative at that point is equal to the slope of the secant line. Roughly that's how that worked. Okay, so if you took a secant line over an interval for a function, you'll find a point within that interval where the slope of the derivative is equal to the slope of the secant line. Well, here we're saying something slightly different, right? We're saying that, if f is continuous, so we assume f is continuous on the interval AB, there is some point C inside AB such that the value of f at C is equal to the average value of the function, okay? And that kind of makes sense. There's an intuitive way to see that. I mean, that's just telling you, if you've got any good old-fashioned function here, f of x, and is continuous on a, b, well, let's eyeball what the average might be. It looks like it's going to tilt a little bit over here. And so if this is here f bar on AB, okay, if this is f bar on AB, okay, that's that right there. Well, what this is telling you is there exists some point C, okay, such that you know, f of c equals f bar there. Okay, that's what that's saying there. All right. So we call this the mean value theorem for integrals because they're related, right? You could sort of show an equivalence between them with using the fundamental theorem of calculus. So let's look at a concrete example then. So for this problem, we want to find the points on the interval 0 to 1 at which this function, 2x1 minus x times 1 minus x, equals the average value, its average value on 0, 1. So what do we do? I mean, the first step is to find the average value, right? So we just basically plug and chug into that formula, and you get that the average value of this function is 1/3 on that interval. Okay, and so now we have a different problem. Let's solve for the point c such that f of c equals 1/3 on 0, 1. And this is pretty straightforward. On the one hand, we have 1/3 equals f of c. Okay, that we're imposing that because we're looking for the points where the function equals 1/3. On the other hand, we plug in c, okay, into our function. All right, so those are the two sort of pieces of information that you're going to use. So over here is everything there that you need. And you'll end up getting this equation, okay? Now it's a quadratic equation, so you'll use the quadratic solution equation, and you'll end up with these possible solutions, which are equal to 0.211 or 0.789. And so that's how we could use both the mean value theorem and the concept of finding average values. And we have just learned yet another application to integration.